Hi, this is Dr. Graves from the CSUN Geography Department and geographyplanet.org. This is part 2 of a video series in which I demonstrate how to do statistical modeling or regression testing using some data about childhood fitness levels and fast food accessibility in Los Angeles County, and we're doing everything in Microsoft Excel. In part 1, we put together what you see here on your screen, which is a series of variables, data that we think, taken together, predict the percentage of fifth graders that tested in the healthy fitness zone for each zip code in Los Angeles. And so I have all of my candidate variables over here to the right, and I have selected what I think are promising variables based on the correlation coefficients that we calculated in a previous video. So I have selected these candidate variables: average household size, percent white people, percent people with a bachelor's degree, the median household income, and this is the location quotient for supermarkets. It's a density of supermarkets. So it's essentially a measure of relative access to supermarkets. Once I have all of these in order, and again, we want anywhere generally between 3, 7, and I'm going to go with 5. We want to click on the Data tab and select the data analysis tools. And once again, you have to install the data analysis tool prior to doing this. From the data analysis tools, find regression, select it, and click OK. The Y input range is the dependent variable, or the effect or the outcome, and that for us is the percentage of children that tested in the healthy fitness zone. And since I selected the header row or the labels, I want to select that and then move down here to the explanatory variables, and those are in these columns. This is the range, and it's going to be all 5 columns of data at the same time, including row 1. Our confidence level is 95, and that's standard, so it's the default. And we're going to have it put on a new worksheet ply, and we'll call this new worksheet ply Model 1. And this is an iterative process, so it generally takes, if you're using Excel, multiple attempts in order to find the 3 to 7 variables that work together most powerfully, most efficiently to predict the outcome variable, in this case fitness percent. I'm going to check on residuals and standardized residuals. And residuals represent the distance between the prediction made by the model and the reality that you see in column C. So it's a sort of observed versus expected. And we will, for this first go through, select normal probability plots so we can take a look at what that looks like. It will help us identify outliers in the data that might be undermining the efficacy or what's called the model fit, where the predictive variables actually predict well the dependent variable. And once you have that, click OK. It will take only a moment. There's the normal probability plot, and that looks about what you would want. There's not odd outliers here, a dot or 2 way off. We won't need to look at that. The important statistic here is the adjusted R squared. Put that in green. And so this roughly interpreted is that we are explaining, using our variables, about 55.4% of the variation in childhood fitness levels is explained by the variables we have chosen. The F statistic is a measure or an indicator of the overall significance of the model, and anything over 1.96 is generally good. And this is 1.005 times 10 to the negative 40, and if we convert that to a regular number, it is 0.00 with a lot of zeros, which means that we can be very confident that this model is actually working. And that's because, in part, we have a lot of observations, 243, which is a large number, and that makes our model more stable. The next thing that we need to really take a look at here is the Tstats for each of our predictive variables. And so here we have all 5 of them, and it looks like we picked pretty well. Average household size worked well. So did percent white, bachelor's degree, median household income, are all effectively contributing to the overall fit of the model. And the only one that is not significant, because it doesn't reach beyond positive or negative 1.96, is the effective supermarket density. And so once again, if we take these variables here, convert them to number, anything that is smaller than 0.05 we would want to keep. So in this instance, we're going to get rid of location quotient for supermarkets in a subsequent. The next thing that we would want to take a look at here is, and I'm going to move these columns of the probability output over a little bit to the right, and I just want to show you how residuals work. So we can come over here back to our original data, copy it out, and I'm going to paste it here. And so observation 1 is zip code 9001. The actual or observed fitness percent is 50.78. The model predicted it should have been 51.58. That is a residual of negative 0.8, and standardized, meaning put on a bell curve, it is negative 0.12. So in this instance, the model did a very good job of predicting the fitness percent, and it should be just a little higher than it is, but it is clearly within range. What I'm going to do is click on the word standardized residuals and sort A to Z, and we find, especially after I apply conditional formatting, that there are, looks like 10 zip codes where the students should have much greater fitness levels than they do based on the conditions in these neighborhoods. I'm going to flip this around and go Z to A, and these are neighborhoods here up that have far greater fitness levels than one would expect given the model's prediction. So in this final part of this tutorial, what I'm going to do is go back to my data. I've rearranged it so that I have, over several tries, figured out which of the variables work together most effectively to explain the level of fitness by zip code. One of the things that I do, I'm scrolling to the bottom here, is that I try to make a mark at the bottom of these columns as I go through iterations of testing. This is sometimes also called stepwise, where you add a new variable and pull a variable out of your model, each time evaluating the utility or the effectiveness of the new variable in the model. I didn't do this all on my own. I have other software, in this case ArcGIS Pro, that does something for me called exploratory regression, where it goes through all of the explanatory variables and rearranges them in multiple ways and tests for model fit. It returns the best model that doesn't suffer from something called variable inflation or collinearity, which is a condition in which the explanatory variables that we use don't correlate with each other too much, where they're explaining each other more than they are the dependent variable, which in this case is fitness. So after cheating and using another software, I have come to the conclusion that unemployment rate, percent brown or Hispanic and black, median age, median income, and the location quotient for fast food, otherwise known as neighborhood fast food density, are the variables that I want to use. So let's do this one more time. Click Data, Data Analysis, select Regression. Okay, the columns of data under consideration are going to remain the same because I didn't add any more than the 5 that I started with, and we'll ask for the residuals, the standardized residual plots, and this time I'm checking off line fit plots. I'm going to call this model 2 and click OK. Here we have the summary output of the model number 2. Taking a look quickly at our model specifications, the adjusted R-square at 61.61, that's outstanding, I think, for this kind of analysis. Our significance variables, F and the significance, are excellent. If I convert that over to a number, we see that it is quite a few zeros there, and the Tstats for each of these is beyond 1.96, either negative or positive, and once again each of the p-value for each of those is really pretty good, including the density of fast food. So for our purposes, we could argue that in addition to the unemployment rate, the percentage of Hispanic and black folks in a neighborhood, the median age of the neighborhood, and the median income of the neighborhood, the density of fast food in a neighborhood all contribute to the level of childhood fitness. These line plots give us an indication of how each of the variables included in our model match up. So this is that scatter plot diagram. With our remaining few moments, I have copied the fitness percent data that function as the observed, and so we can take a look at it comparing to the prediction made by the model. Once again, we'll sort the data by the standardized residuals, coming up with these that are more than essentially 2 standard deviations below. Rather than belaboring this point, I did want to bring in this map that has essentially the exact same data, and the value of seeing this in a GIS is that these zip codes that appear in blue are those zip codes that the children are testing still below what the model predicts. And so those areas are places that we probably really should examine, and maybe we can learn lessons from these places in red. The children are still testing above what one would expect. I want to leave off here because if you want to do regression in Excel, it's a good starting place, but it is challenging to do a robust analysis that considers all of the possible pitfalls of modeling unless you have a more sophisticated software designed for this, like ArcGIS Pro